Why is there fire only on Earth, but nowhere else in the universe? You heard that right. So far, aside from Earth, scientists have not found fire anywhere else in the universe. At first glance, this might seem strange. What about the sun? What about the mythical planets that rain fire, or worlds filled with volcanoes and violent lightning storms? Surely those count, don't they? The truth is, not quite. None of those phenomena, strictly speaking, are what we commonly define as fire. So then, what exactly is fire? Some people believe fire is a form of plasma, the so-called fourth state of matter. After all, if you bring a statically charged object close to a flame, the flame wiggles and bends, showing that it contains electrically charged particles. But does that mean fire is definitively plasma? Not necessarily. Consider the difference between flames on Earth and those observed aboard the International Space Station. In microgravity, flames form strange, spherical shapes. Why is that? And why are the hottest, most intense flames usually blue in color? Where does that blue come from? Even more intriguingly, some flames are nearly invisible to the naked eye. Humanity has been using fire for thousands of years, and yet many of its mysteries remain unsolved. So what is this seemingly familiar, yet elusive thing we call fire? Why does it appear to exist only on Earth? And how is it connected to life itself? From basic science, we know that fire is the result of a combustion reaction, when fuel burns in the presence of oxygen. But fuel doesn't just refer to gasoline or diesel. In fact, anything combustible, wood, paper, cloth, can serve as fuel. And oxygen typically refers to the oxygen in Earth's atmosphere. Yet combustion can still occur without atmospheric oxygen if there's an oxidizing agent present, certain chemicals that support combustion independently. So when we say something burns, what's really happening is a rapid chemical reaction between fuel and an oxidizer, releasing large amounts of energy, mostly in the form of heat. However, even if you place fuel and oxygen together, fire doesn't automatically ignite. The fuel must reach a certain ignition temperature, known as its flash point, to catch fire. Different materials have different ignition temperatures. Only when the right temperature is achieved can combustion begin. That's why we need matches or lighters to get a fire going. Once it starts, the heat produced by the flame continues to ignite the remaining fuel, allowing the fire to sustain itself. Thus, fire needs three essential elements: fuel, oxygen, and heat. This is commonly called the fire triangle. You might recall this concept from workplace fire safety training. Remove any one of the three elements, and the fire goes out. For example, water extinguishes fire by removing heat. A fire blanket smothers it by cutting off oxygen. Keep this model in mind. It's important. Let's take a closer look at fuel first. Most fires on Earth burn organic materials, in other words, stuff that comes from living things. Gasoline and diesel are fossil fuels, derived from the remains of ancient organisms. Wood, paper, and fabric come from plants. Even plastics and synthetic fibers are typically made from petrochemicals, again based on fossil resources. Now, what about oxygen? In Earth's early atmosphere, there was almost no oxygen. The oxygen we breathe today was first produced by cyanobacteria, photosynthetic microorganisms. In fact, all the oxygen in our atmosphere can be traced back to biological activity. In other words, two of the three essential elements of fire, fuel and oxygen, on Earth are the products of life. Fire, in a sense, is only possible here because life made it possible. But what about the rest of the universe? Does that mean only life can create fuel? Not exactly. There are many sources of non-biological fuel in space. Take methane, for instance. It's abundant across the cosmos and is an excellent fuel. Titan, one of Saturn's moons, has massive quantities of methane. Methane has also been found on other planets and moons. The problem? Titan lacks oxygen, so even with plenty of fuel, fire cannot ignite. Hypothetically, if a natural mechanism transported oxygen to Titan, perhaps flames could ignite, but they wouldn't last long. Once the oxygen or the fuel runs out, the fire dies. It's even possible that some celestial bodies in the distant past did witness fire. But if their fuel and oxidizers have long since been depleted, the fire would have vanished too, leaving behind no trace for us to observe today. So perhaps, somewhere, sometime, fire flickered briefly in the cosmos. But as of now, Earth remains the only known place in the universe where fire still burns, and it does so because of life. The fire we know and rely on is more than a physical phenomenon. It's a signature of life's complex influence on a planet. And until we find both life and its environmental traces elsewhere, Earth's fire may remain uniquely ours. Why fire exists only on Earth and what makes it so unique. Here on Earth, things are completely different. The fuel and oxygen required for fire are continuously being produced by life. Microorganisms and especially plants, such as trees that carry out photosynthesis, play an absolutely vital role in this process. They are the sources of wood, coal, paper, fabric, and many other fuels. Even animals, which store energy in their bodies, ultimately rely on plants. Fossil fuels, derived from ancient animals, also trace their energy origin back to plant life. Plants use minerals from the soil, water, and carbon dioxide from the atmosphere to create organic matter, powered by sunlight. During this process, they release oxygen continuously. In short, fire exists on Earth because solar energy is constantly being absorbed and transformed by life into fuel and oxygen. Put simply, life enables fire to keep burning on Earth. To date, we've found no signs of life on other planets, and that may well explain why we've also never found fire elsewhere in the universe. Now you might be thinking, but what about the sun? Isn't it burning? While it's a common phrase, the sun is not burning in the way we understand fire. The sun is rich in hydrogen, a flammable element, yes, but fire needs oxygen, and there's no oxygen in the sun. The sun's energy doesn't come from burning hydrogen, it comes from nuclear fusion. In the sun's core, hydrogen nuclei fuse to form helium, releasing immense energy in the process. But this nuclear fusion only happens deep in the sun's interior. The energy it produces takes time to reach the surface, and then travel to Earth. Now consider this. When an object is heated to extremely high temperatures, it glows. A glowing stove coil or the filament inside a light bulb is an example. This type of light is called thermal radiation, or blackbody radiation. Because of the extreme heat generated by fusion at the sun's core, the outer layers become incredibly hot and emit light, not from fire, but from radiation. The sunlight we see, like the light from all stars, is the result of this radiation, not combustion. Volcanoes too might appear to emit fire, but that's mostly lava, molten rock, and mud glowing from heat. That glow is again thermal radiation. In rare instances, certain volcanic gases might ignite upon contact with atmospheric oxygen, creating small flames. But even that relies on Earth's unique oxygen-rich atmosphere. Now let's take a closer look at fire itself. Why are some flames blue while others are yellow? Is fire really a plasma? Why does it look the way it does? As mentioned earlier, fire is the result of a rapid chemical reaction between fuel and oxygen, producing heat as its main byproduct. But we only see flames when part of that heat is converted into visible light. If the energy isn't converted to visible wavelengths, fire can be burning without being seen. This is called an invisible flame. So how does heat turn into visible light? There are several ways. First, let's talk about yellow flames. Remember blackbody radiation? Common fuels like wood, wax, or natural gas are made of carbon and hydrogen-based compounds. When these burn, they typically turn into carbon dioxide and water vapor. But in many cases, the combustion is incomplete, leaving behind tiny carbon particles in the flame. In these incomplete burns, large amounts of soot or carbon particles are heated to high temperatures and glow. This glow is what gives us the familiar yellow flame. So, a yellow flame is essentially a glowing cloud of tiny hot soot particles. Now for blue flames. If combustion is particularly clean, with little to no leftover carbon, then there are no glowing soot particles. Instead, the blue light comes from emission spectra produced by certain molecules in the flame. These molecules emit light at specific wavelengths. When atoms are heated, their electrons absorb energy and jump to higher energy levels. As they fall back, they release this energy as light. The color of this light depends on the difference between energy levels. Each element has its own unique emission spectrum. Molecules and chemical radicals, smaller fragments of burning fuel, also have emission spectra. Some of these fall in the visible blue range. That's why clean burning fuels like methane or alcohol produce a blue flame. In short, the color of fire depends on how cleanly it burns and what it's burning. A fire is only visible when some of its energy is converted into visible light. Otherwise, the flame may be nearly invisible. Fuels like hydrogen, methane, and alcohol burn with such clean combustion that their flames are extremely faint, sometimes barely visible to the naked eye, except under dark backgrounds. So while fire may seem simple, it is a deeply intricate phenomenon, made possible by a delicate balance of chemistry, energy, and life. On Earth, it flourishes. Elsewhere in the universe, it may await the spark of life to ever burn again. Why do flames rise upward on Earth? And what is fire, really? On Earth, flames always rise upward, a seemingly obvious fact that is actually the result of a combined effect between gravity and atmospheric pressure. When air inside the flame is heated, it expands and becomes less dense. This lighter hot air rises immediately, creating a vacuum beneath it. Cooler surrounding air quickly rushes in from below to fill the space. This incoming air not only restores balance, but also brings in fresh oxygen, an essential element that fuels the flame and causes it to burn even more intensely. This upward flow of hot air stretches the flame into its familiar shape and helps carry away combustion byproducts. However, in a microgravity environment, like aboard the International Space Station, this effect disappears. With little or no gravity, hot air doesn't rise, and the combustion gases remain trapped around the flame. As a result, the flame doesn't stretch upward, but instead takes on a spherical shape. With no effective circulation to remove exhaust or bring in fresh oxygen, the flame suffocates in its own waste and may quickly extinguish. This brings us to an interesting question: is fire a form of plasma? In reality, plasma, the fourth state of matter, only forms under extremely high temperatures, typically above 3000 degrees Kelvin 400 degrees. At such temperatures, atoms lose their electrons and become charged ions. But most everyday fires burning wood, candles, or even gas stoves only reach around 1500 degrees Celsius, 2700 degrees, far too low to create plasma. In special cases, such as with an oxyacetylene welding torch, the flame can exceed 3000 degrees Celsius, and in those extreme conditions, a small portion of the flame may enter a plasma state, but only partially, not entirely. That said, during combustion, fuel molecules break down into smaller fragments called free radicals, and some of these carry electrical charges. This is why a flame can bend when exposed to an electric field. However, this doesn't mean the flame is entirely plasma. It just contains some ionized particles. In fact, scientists do not define fire as a specific state of matter. Rather, fire is a dynamic chemical process, an observable phenomenon. It results from complex interactions between fuel, oxygen, and heat, also known as the fire triangle, and includes the emission of heat and visible light. Fire isn't a substance. It's an unfolding chain of reactions involving the transformation of energy and matter. What appears to be ordinary, the flickering glow of a flame, is in fact a reflection of the intricate laws of physics and chemistry. Fire is born of life on Earth, a visible testament to the unique conditions that make our planet special. That small match strike, or the soft dance of fire in the night, is more than just light and warmth. It is a bridge between biology, chemistry, physics, and the cosmos. Today, we've only peeled back a corner of fire's mystery, but this glimpse is enough to show that the journey of understanding fire, from the microscopic spark to the vastness of the stars, is far from over. And perhaps, from this small curiosity, a new flame will ignite within us all, the fire of wonder for the unknown.